Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends, to your younger brothers and sisters who would want to take up engineering in the future, and to your relatives. That's one way you can keep me going, inspired, and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe.
Hello everyone, let's have another problem on structural analysis, specifically on prop beams. And this time, let's solve this I'll present two solutions here. One using the superposition method and the other one by slope deflection equations, concepts on slope deflection equations. So for the prop beam shown subjected to the loading 8 W kilonewton per meter and A equals L equals 8 meters. So meaning to say the loading is over the entire span. And for part B, W is 36 kilonewtons per meter, A is 6 meters, and B is 2 meters. So that means L is 8 meters in the second part. Compute the external support reactions. So for our solution, let's call the reactions at A as AY, AX is 0 obviously, and the moment is, let's assume clockwise, because clockwise moment in slope deflection equation is positive. And this is the loading, and at B we have RB, reaction only. So note that the in the first part, it is the loading is over the entire span, and the deflection at the end, if roller support B is removed from superposition method, is W EI delta due to load is WL to the fourth over 8. Remember that. So you look at also the derivation of this in structural analysis 1 point something, and just look at the playlist. So EI due to the deflection at B due to the load WL to the fourth over 8, while due to the concentrated load or reaction at B, it will deflect upward. And the deflection here is EI delta B due to the reaction is equal to reaction or the force L cube over 3. So EI delta B due to reaction is RB L cube over 3. Equating, this is the absolute value, this is downward deflection, but the positive absolute value should be equal to that because there's no net support movement at B. So W RBL cube over 3 equals WL to the fourth over 8. So from here, we can now compute RB, which is 3/8 WL. So upward. So that's the reaction at B when the beam is entirely loaded. Then for MA, we sum up moment about A. So MA plus W times L over 2 equals RB times L. So MA plus W times L over 2 equals RB, which is 3/8 WL times moment arm about A is L. So 3/8 WL squared minus 1/2 WL squared is negative 1/8 WL squared. So MA is negative WL squared. So meaning to say it should be counterclockwise. So it is clockwise and it is negative WL squared over 8. Then finally for AY, we sum up moments about B so that uh, we can check the equilibrium by summing up forces Y. So the expected value of AY is 5/8, supposedly WL, and we can find that by summing up forces vertical, but I will not do that. I just use uh, moment equation so that we can use summation versus y for checking, and so that we can involve MA to make sure that these answers are correct. So summation moment about B equals 0, AY times L plus MA, which is negative WL square over 8, equals moment of the load, which is WL times L over 2. So AY times L plus negative WL square over 8 equals moment of the load WL times L over 2. So 1 half WL square plus 1/8 WL square is 5/8 WL square divided by L. So AY is 5/8 WL, and it is upward as expected. So that 3/8 WL plus 5/8 WL is WL, the total load. So that's it for the first part. For the second part, moment A, or this is the other way, other solution for moment at A. Fixed moment at A minus 1 half fixed moment at B. This is the derived formula when the far end B is roller support or pin support where the moment is 0. You just look at the derivation from slope deflection equations. So, fixed moment A is, it is counterclockwise, so negative WL square over 8, and fixed moment B is negative WL square over 12, and fixed moment at B is positive WL square over 12 when the beam is entirely loaded as shown in the figure. So this is the direction. This is negative because it is counterclockwise from slope deflection equation, but this is supposed to be the positive moment, but we just rely on slope deflection equation. That's why from slope deflection equation, clockwise rotation, clockwise moment would be positive. That's the sign convention from slope deflection equations. Then at the right side, because this is the actual fixed moments, is clockwise, so it is positive WL square over 12. So moment at A is negative WL square over 12 minus 1 half of positive WL square over 12. So this is negative 112 WL square, then negative 1 over 24 WL square. We'll get negative WL square over 8. Then the rest of the processes would be the same as the previous. We have to apply equations of statics. So I'm just verifying that the moment at A by another approach is the same. Then we proceed to part B. So A is, these are the reactions not equal to this because this is another case. Then reaction at B, let's just call it RB also. But A this time is 6 meters, B is 2 meters. So by superposition method, if B is removed, by the way, W is 36 kilonewton per meter. So this would be the deflected shape. This portion is straight. Call this deflection delta 1 and this part delta 2. And the slope here is theta 1, which is the same because this is straight part. This part is not loaded. So call that delta 2. So remember that if we call this theta 1, tangent of theta 1 equals theta 1 itself because theta 1 is very small. And tangent theta 1 is theta 1 equals opposite delta 2 over 2. So therefore delta 2 is 2 times theta 1. So part B, AI delta B due to the load is delta 1 plus delta 2. Delta 1 is moment at the wall, M1, L1 square divided by N plus 2, where N is 2, second degree, because the moment diagram by parts of this uniform loading would be second degree. And delta 2 is, as mentioned, 2 times theta 1. Tangent theta 1 is theta 1 itself equals delta 2 over 2 meters. So that's why it is 2 theta 1. Formula for theta 1 is M1 L1 over N plus 1. So AI delta B due to the load is M1 L1 square, where L1 is 6 over n plus 2 times m1 L1 over n plus 1, where n is again 2. So m1 is equal to moment at the wall, so it is 36 times 6 times 3. 36 times 6 times 3 moment of the loading about this fixed wall. So m1 equals 648 kilonewton meter. So substitute here, L1 is 6 and n is 2. So AI delta B due to the load is 648 times 6 squared over 2 plus 2 times 648 times 6 over 2 plus 1. So due to the load, the deflection is downward, and the value of BI delta B due to the load is 8424 kilonewton meter cube. Then due to the reaction at B, it is reaction at B L cube over 3, just like here. Reaction at B L cube over 3, where L is 8 because B is acting at the other support B. So we equate the two. So 8424 equals RB times 8 cube over 3. So from here, we can now solve for the reaction at B, and it is equal to 49.36 kilonewtons upward. Having known B, let's solve for MA. Let's assume clockwise again. We sum up moments about A equals 0. So MA plus 36 times 6 times 3 equals RB times 8. So MA plus 36 times 6 times 3 equals RB 49.36 times 8. So from there, we can solve MA, and MA is equal to negative 253.1 kilonewton meter. Then for AY, just use moments summation. So summation moment at B, so that we can check equilibrium summation versus Y. We use that for checking, and so that we can involve NA to make sure that NA is really correct. So AY times 8 plus MA, which is negative 253.1, equals moment of the load, which is 36 times 6, and the moment arm is half of 6.3 plus 2, 5. So the moment arm is 5. So AY times 8, summation moment B equals 0, plus moment A, negative 253.1. AY times 8 is clockwise, so plus clockwise MA, but we carry the sign, equals 36 times 6 times 5. So solving for AY, which is also upward, is equal to 166.64 kilonewtons upward. So that 49.36 plus 166.64, that's the 216, then minus 36 times 6, so that would be 0. So that checks. So another approach, we'll just compute MA. So MA is fixed moment at A minus 1/2 fixed moment at B for prop beams, or for when the far end has roller or pin support, or when the far end has 0 moment. So as again, you look at the derivation from slope deflection equations. So fixed moment at A due to concentrated load is negative, just like this case here, negative PAB squared over L squared. That's the formula. So let's have that strip so that we can have differential P. It is 36 dx, the area, differential area of the strip. The thickness is dx and the height is 36. So differential P is differential area dx, or dx times 36, or 36 dx. We'll call this distance x, and the distance of the centroid of this strip, or dp, from B is 8 minus x. 8 meters L, then minus x. The formula, fixed moment formula at A, is negative PAB squared over L squared, because it is counterclockwise, expected counterclockwise at the right side, clockwise, so positive at the right side. And fixed moment B is just, we just interchange the squared factor, so PA squared B over L squared, and positive. So substitute, because this is in differential form, so we use integration here. So A is the distance of dp from the left, which is x, and b is distance of p from the right, so 8 minus x. So fixed moment A is negative integral of 36 dx times x times 8 minus x squared over 8 squared. So using your calculator, because it can evaluate integration from limits, by the way, of x is from 0 to 6. So 6 meters, A is 6. And that is equal to negative 182.25 kilonewton meter. Likewise, fixed moment B is positive. So this is now squared, and this is 8 minus x to the 1. So fixed moment B equals integral 0 to 6 of 36 dx x squared, quantity 8 minus x all over 8 squared. So therefore, fixed moment B is equal to 141.75 kilonewton meter. Substitute MA equals negative 182.25 minus 1 half of positive 141.75. And we'll get MA, which is the same as that, negative 253.1 kilonewton meter. So the rest of the solution for RB and AY will be equation of statics. So I'm just verifying that the answers are the same by these two approaches. So that's it for this video. I hope that you learned something for you to master structural analysis.